All right, so when we talk about what makes plants grow, our minds usually jump to things like nitrogen and phosphorus, right? But there's another player, a kind of silent guardian in our soil that's just as crucial for the food we eat. Today, we're pulling back the curtain on the hidden world of potassium. Scientists and farmers have a nickname for it. They call it the quality element. And there's a really good reason for that. Potassium is what gives our food its quality. It's behind the sweetness in fruit, the strength that helps a stalk of corn stand up to the wind, and a plant's basic ability to handle stress. Now, here's what's so fascinating about potassium. Unlike a lot of other nutrients, it's not actually a physical building block. It doesn't become part of the plant's walls or leaves. Instead, you should think of it as a mobile regulator. It's like a tireless supervisor constantly moving around inside the plant, making sure all the important jobs get done right. And it is a very busy supervisor. I mean, potassium is responsible for managing more than 60 essential enzyme reactions inside a single plant. This one element is controlling everything from water balance, literally opening and closing tiny pores on the leaves, all the way to transporting sugars to make sure grains fill out. It's the engine that drives a plant's health. So it's obviously a huge deal for plants. Which brings us to a pretty critical question, one that really gets to the heart of our food security. What on earth happens to our crops, to our entire food system, when this silent guardian just isn't there anymore? To figure that out, we need to look at the soil itself. And the best way to understand potassium in the soil is to think of it like a bank account. An account with 4 different pools of money, each with a different level of accessibility. And wow, this chart really lays out the fundamental challenge we're facing. As you can see, a staggering 98% of all the potassium in the soil is what we call mineral K. It's completely locked away inside rocks and minerals. That means only about 2% is even potentially available for a plant to use. So let's break down this bank account. First, you've got that mineral K. That's the long-term vault. It's released incredibly slowly over geological time. Then you have fixed K, which is like slow-release bonds, kind of trapped in clay layers. Now, the one that really matters for farmers is exchangeable K. That's the checking account, where plants get most of their daily potassium. And finally, there's solution K. That's the cash in your pocket, ready to use, but also really easy to lose if it rains. The key thing is all these pools are constantly trying to stay in balance with each other. But here's the problem. Modern agriculture, with its high-yield crops, has been making a massive and frankly unsustainable withdrawal from this bank account. We're taking potassium out way, way faster than nature can put it back in. I mean, just look at these numbers. It's pretty shocking. Natural processes like the weathering of rocks might add about 3 kilograms of potassium to a field each year, but a big crop of corn, it can pull out over 250 kilograms. This isn't just a gap, it's a chasm. We are draining the account. And this isn't some far-off, abstract problem. It's having real-world consequences right now. In huge agricultural regions like South Asia, this negative balance is leading to something researchers call hidden hunger in crops. The plants might look okay, but on the inside, they're weak. They don't have that internal strength to fight off diseases or survive a drought, which are huge threats to our global food supply. So if you're managing a bank account, you need to be able to check the balance, right? You have to know what's in there. So how do farmers and scientists actually read the soils statement to figure out what's really available for their crops? The process is actually pretty clever. In the lab, they take a soil sample and use ammonium ions to basically kick the available potassium off the little soil particles it's clinging to. Then, a special machine called a flame photometer measures exactly how much potassium was released. It's a snapshot of what's in the checking account. But, reading that bank statement isn't always straightforward. For instance, some types of clay can hold onto potassium so tightly that the lab test can't see it all, so it underestimates the balance. That's why farmers also have to be detectives in the field, looking for real-world signs like scorching along the edges of leaves. That's a classic distress signal from a plant that's starved for potassium. Okay, so we've laid out a pretty serious problem, a bank account that's being drained. But here's the good news, this is solvable. There are smart investment strategies we can use to start reinvesting in our soil's health and build up that natural wealth for a much more resilient future. So what are these smart investments? Well, it really comes down to 3 key things. First, being smart about choosing the right fertilizer for specific conditions. Second, and this one is a game changer, recycling the crop residues. And third, we're entering this amazing new frontier of using biological allies. tiny microbes that can help us out.
Let's just focus on that recycling idea for a moment, because the impact is just staggering. By simply leaving the stalks and leaves on the field after harvest, we can recycle 60 to 80% of the potassium the plant used. It's a simple, incredibly powerful, nature-based way to start closing that huge replenishment gap.
And then you have these little critters, potassium-solubilizing bacteria, or KSBs. These microbes do something that sounds like science fiction. They release these special acids that can literally dissolve the surface of rock minerals, cracking open that giant 98% vault we talked about earlier. It's like having an army of microscopic miners unlocking trapped nutrients for the plants. It's a high-tech solution that's also completely natural. So, it all comes down to this. For too long, we've treated our soil's potassium like it's an infinite resource. But it's not. It's a finite bank account that's governed by a very strict budget. The quality and the security of our entire food system depends on keeping that budget balanced. So it leaves us with one final, and I think, pretty vital question. Is our soil's bank account truly solvent?